Welcome to a journey that dives deep into the essence of life itself, water. Before we embark on this exploration, we must share a vital warning with you. You might be tempted to skip ahead or leave, but we urge you to stay with us. The information we're about to share is foundational, intricate, and enlightening. It's the key to understanding the entire series that follows. From the solid particles that lurk unseen to the very essence of what makes water safe or dangerous, we'll uncover truths that are both fascinating and alarming. This is not just about science, it's about our health, our environment, our future. So, we ask for your full attention, your curiosity, your willingness to explore with us. Remember this warning, for what you learn here will change the way you see the world around you. Now, let's begin our journey into the world of water cleanliness.
Water, often referred to as the essence of life, plays a pivotal role in sustaining not only human existence, but also the entire ecosystem. Its applications are manifold, ranging from nourishing our bodies to powering various industrial processes. However, the sanctity of this vital resource is increasingly being threatened by pollution and contamination. The cleanliness of water is paramount for maintaining public health, as impure water can lead to a plethora of diseases and infections. Moreover, polluted water adversely affects aquatic life, leading to ecological imbalances and threatening biodiversity. The industrial discharge of toxic substances, agricultural runoff laden with pesticides, and improper waste disposal are some of the primary culprits that compromise water quality. The urgency to address this issue has never been more pronounced, as the implications of contaminated water extend beyond health concerns to socioeconomic challenges and geopolitical tensions. Ensuring access to clean and safe water, therefore, is not merely a matter of environmental stewardship, but a fundamental human right that underpins the very fabric of our society. Governments, industries, and individuals must collaborate to implement stringent regulations, innovative purification technologies, and responsible consumption practices to safeguard this irreplaceable resource for future generations. Importance of water cleanliness. Clean water is essential for our health, environment, and economy. Let's delve into why. Clean water is not merely a refreshing beverage, but a fundamental necessity for our physiological well-being. Its role in our daily lives is multifaceted, encompassing various biological functions that sustain life. Firstly, water aids in digestion by facilitating the breakdown of food, allowing nutrients to be absorbed efficiently. It acts as a solvent for essential vitamins and minerals, transporting them to different parts of the body. Secondly, water plays a crucial role in thermoregulation, helping to maintain body temperature by dissipating heat through perspiration. This function is vital for metabolic processes and maintaining homeostasis. Furthermore, water contributes to the health and appearance of our skin by keeping it hydrated and supple. Dehydration can lead to dry, flaky skin and exacerbate conditions like eczema. On the other hand, the quality of water we consume has direct implications on our overall health. Contaminated water, laden with pathogens and toxic substances, can lead to severe illnesses such as cholera, typhoid, and dysentery. These diseases, often prevalent in regions with poor sanitation and inadequate water treatment facilities, can be fatal if left untreated. The importance of clean water extends beyond personal health to public health concerns. The contamination of water sources can lead to widespread outbreaks, straining healthcare systems and leading to socioeconomic challenges. Moreover, the presence of heavy metals and industrial pollutants in water can have long-term health effects, including neurological disorders and reproductive issues. Ensuring the purity and safety of water, therefore, is not just a personal responsibility, but a collective one. It requires concerted efforts from governments, industries, and communities to implement stringent regulations, invest in water treatment technologies, and promote responsible consumption practices. Educational initiatives to raise awareness about water conservation and hygiene are equally vital. In reality, clean water is more than a basic human need. It is a cornerstone of our health and well-being. Its significance transcends individual benefits to encompass broader societal implications. The pursuit of clean water is a complex and multifaceted challenge that demands a holistic approach, integrating scientific innovation, regulatory oversight, community engagement, and individual responsibility. The quality of the water we consume is a reflection of our values, our stewardship of the environment, and our commitment to future generations. Ensuring access to clean water is not merely a health imperative, but a moral and ethical obligation that defines our humanity. Access to clean water transcends the boundaries of individual health and becomes a cornerstone of community well-being, shaping the very fabric of society. In regions where clean water is readily available, the benefits are manifold and far-reaching. Firstly, the provision of clean water leads to lower rates of illness, particularly waterborne diseases, that can ravage communities lacking proper sanitation and water treatment facilities. The reduction in illness not only enhances the overall health of the community, but also alleviates the burden on healthcare systems, freeing resources for other essential services. Secondly, access to clean water has a direct correlation with educational attainment. Children in areas with clean water are more likely to attend school regularly, as they are less prone to diseases that can cause absenteeism. Furthermore, the availability of clean water in schools encourages hygiene practices, creating a conducive learning environment. This, in turn, contributes to higher literacy rates and educational achievements, laying the foundation for a skilled and knowledgeable workforce. Thirdly, clean water acts as a catalyst for economic growth. It supports various sectors, including agriculture, manufacturing, and tourism, by providing a reliable and safe water supply. Communities with access to clean water attract investments and foster entrepreneurship, leading to job creation and income generation. Conversely, the absence of clean water can stifle economic development as industries struggle with unreliable water sources and healthcare costs soar due to increased morbidity. Lastly, clean water enhances the overall quality of life within a community. It supports recreational activities, cultural practices, and social interactions, fostering a sense of belonging and cohesion. The availability of clean water is often a reflection of social equity, as marginalized and impoverished communities are more likely to suffer from water scarcity and contamination. So, clean water is not merely a personal necessity, but a communal asset that binds us together. It is a symbol of progress, equality, and human dignity, reflecting our collective responsibility towards each other and the environment. The pursuit of clean water is a shared endeavor that requires collaboration, empathy, and foresight, recognizing that the health and prosperity of one community are intrinsically linked to the well-being of all. The provision of clean water is not just an infrastructural challenge, but a moral imperative that defines our commitment to social justice, sustainability, and a future where no one is left behind. Water, often described as the lifeblood of our planet, plays an indispensable role in sustaining the intricate web of life that constitutes our ecosystem. Its significance goes beyond human consumption, as it nourishes plants, supports wildlife, and maintains the delicate equilibrium of nature. The vitality of clean water can be observed in various ecological contexts. In terrestrial ecosystems, it supports plant growth, providing hydration and transporting essential nutrients through the soil. This, in turn, sustains herbivores and, consequently, the entire food chain. In aquatic ecosystems, clean water is the very essence of life. It provides a habitat for a diverse array of organisms, from microscopic plankton to majestic whales. The quality of water in these environments determines the health of fish populations, coral reefs, and other aquatic life forms. Polluted water, laden with solid particles, chemical contaminants, or excessive nutrients, can have catastrophic consequences. For example, the introduction of toxic substances can lead to fish mortality, disrupt reproductive cycles, and cause deformities in aquatic organisms. Nutrient pollution, often stemming from agricultural runoff, can trigger harmful algal blooms, depleting oxygen levels and suffocating marine life. Furthermore, water pollution affects avian species that rely on aquatic habitats for feeding and nesting. The contamination of water bodies with oil, plastics, and other pollutants poses a direct threat to birds, leading to loss of plumage, poisoning, and even death. The ripple effects of water pollution extend to terrestrial wildlife that depends on clean water sources for drinking and bathing. The protection of water cleanliness, therefore, transcends human-centric concerns and becomes an imperative for planetary stewardship. It is about preserving the intricate relationships and dependencies that define our biosphere. The degradation of water quality not only disrupts individual species, but can lead to the collapse of entire ecosystems, altering natural processes like nutrient cycling and climate regulation. Safeguarding the cleanliness of water is a complex and multifaceted challenge that demands a holistic and integrated approach. It requires recognizing the interconnectedness of life on Earth and embracing a paradigm that values ecological integrity alongside human well-being. Protecting water cleanliness is not merely an environmental issue. It is a profound ethical responsibility that reflects our reverence for life in all its diversity and complexity. The pursuit of clean water is a testament to our commitment to a sustainable future, where the harmony of nature is celebrated, respected, and preserved for generations to come. Water cleanliness is a concern that transcends geographical boundaries, cultural divides, and political ideologies. Its significance is felt on a global scale, influencing not only the health of individual communities, but the very stability and resilience of our planet. The interconnectivity of water systems means that pollution in one region can have far-reaching consequences, affecting weather patterns, ocean currents, and atmospheric conditions. For example, polluted water bodies can alter the thermal properties of oceans, influencing the circulation of currents that regulate climate. This, in turn, can lead to unpredictable weather phenomena, exacerbating natural disasters like hurricanes and droughts. Furthermore, water pollution contributes to climate change by releasing greenhouse gases, such as methane, from decomposing organic matter in contaminated water bodies. This not only accelerates global warming, but disrupts ecosystems that act as carbon sinks, such as wetlands and mangroves. The loss of these vital habitats further compounds the environmental challenges we face, creating a vicious cycle of degradation and instability. The global nature of water cleanliness necessitates a concerted and collaborative approach. It requires nations to look beyond their immediate interests and recognize the shared responsibility of preserving this invaluable resource. International agreements, regulatory frameworks, and technological innovations must be leveraged to address the complex and multifaceted challenges of water pollution. Collaboration between governments, industries, research institutions, and civil society is essential to develop and implement solutions that are both effective and sustainable. Investments in research and development to create advanced water treatment technologies, coupled with educational initiatives to promote responsible consumption, are vital components of a global strategy. Moreover, the integration of traditional knowledge and local practices can provide valuable insights and context-specific solutions, fostering a sense of ownership and community engagement. In conclusion, ensuring water cleanliness is a global imperative that demands a holistic and inclusive approach. It is a reflection of our collective consciousness our empathy towards fellow human beings, and our reverence for the earth. The pursuit of clean water is not just an environmental or economic challenge. It is a moral and ethical undertaking that defines our legacy as stewards of this planet. It is a testament to our ability to transcend differences and unite in a shared commitment to a future where water, the source of all life, is cherished, protected, and celebrated for its intrinsic value and universal significance. The path towards clean water is a journey towards a more compassionate, resilient, and harmonious world, where the dignity of life and the sanctity of nature are upheld as inviolable principles. This series is a comprehensive exploration of water cleanliness. Here's what you can expect. Solid particles, understanding what they are, why they're harmful, and how to detect them. Chemical and biological contaminants, uncovering the hidden dangers in our water. Global perspectives, examining water cleanliness around the world. Community involvement, how you can make a difference. We invite you to stay with us as we dive into these topics and more. Together, we'll uncover the truths about water cleanliness, empowering you to make informed decisions and take meaningful actions. Now let's begin our detailed exploration.
Introduction to solid particles in water. Solid particles in water refer to the various suspended or dissolved elements present within a water body. These particles can vary widely in size, ranging from microscopic entities to substances visible to the naked eye. Understanding these particles is essential for assessing water quality and determining its suitability for various uses. Suspended solids and cleaning methods. Suspended solids include materials like silt, clay, algae, and plankton. These particles are typically larger and can often be seen floating within the water, contributing to the water's turbidity and making it appear cloudy or muddy. They can originate from natural sources like soil erosion or human activities such as industrial discharge. Cleaning suspended solids requires specific methods. Sedimentation, allowing particles to settle at the bottom of a tank or container, often used for larger particles. Filtration, utilizing sand or activated carbon filters to capture smaller suspended particles. Chemical treatment, using coagulants to bind particles together, making them easier to filter out. Biological treatment, employing organisms to consume or break down organic suspended solids like algae. Dissolved solids and cleaning methods. Dissolved solids encompass minerals like calcium, magnesium, and various salts. Unlike suspended solids, these particles are dissolved in the water and are not visible. They often come from natural geological processes, and their presence can affect the taste and hardness of the water. Removing or reducing dissolved solids requires different techniques. Distillation, boiling water and condensing the steam, leaving behind dissolved solids. Conclusion, and reverse osmosis, using a semi-permeable membrane to filter out both dissolved and suspended solids. Water softening, employing ion exchange resins or lime softening to remove specific minerals like calcium and magnesium. Both suspended and dissolved solids present unique challenges in water treatment. The selection of appropriate cleaning methods depends on the type of solid, its source, and the desired water quality. By understanding these distinctions, water treatment facilities and individual households can implement effective strategies to ensure clean and safe water. Solid particles in water can be broadly classified into two main categories: organic and inorganic particles. This classification is vital as it helps in understanding the source, nature, and potential impact of the particles. It also aids in their identification and treatment, ensuring that appropriate methods are used to maintain water quality. 2. Organic particles. Organic particles in water include substances derived from living organisms. This category encompasses plant debris, microorganisms like bacteria and algae, and sometimes even small aquatic creatures. Organic particles can originate from natural processes such as decay or human activities like agricultural runoff. They may contribute to water's color and taste, and can sometimes pose health risks if not properly treated. Common methods to treat organic particles include biological treatment, where specific organisms are used to break down the organic matter, and filtration to remove larger debris. Filtration, employing filters to capture larger organic debris such as plant material. Ozonation, using ozone to oxidize and break down organic compounds. Biological treatment, utilizing specific organisms to break down organic matter. The choice of method depends on the type and concentration of organic particles, as well as the intended use of the water. Inorganic particles. Inorganic particles consist of metals, minerals, and other non-living substances. These can include elements like calcium and magnesium, which contribute to water hardness, or potentially harmful metals like lead and mercury. Inorganic particles may come from natural geological processes, industrial discharge, or mining activities. Treatment methods for inorganic particles vary based on the specific substance and may include chemical treatment to neutralize or precipitate the particles, or advanced filtration methods like reverse osmosis. Reverse osmosis, using a semi-permeable membrane to filter out inorganic solids. Distillation, boiling and condensing water to leave behind dissolved inorganic solids. Chemical treatment, applying specific chemicals to neutralize or precipitate particles. The treatment of inorganic particles requires careful consideration of the specific substances present and their potential impact on water quality. Considerations in treatment include the classification of solid particles into organic and inorganic categories provides a foundational understanding for water treatment professionals and environmental scientists. By recognizing the distinct characteristics and sources of these particles, targeted treatment methods can be applied. This ensures not only the safety and palatability of the water, but also the protection of aquatic ecosystems. Continuous research and technological advancements in water treatment are essential to address the diverse and ever-changing nature of solid particles in water, promoting sustainable water management practices. Water, the essence of life, is often taken for granted in its purity and composition. Yet the unseen particles that reside within can tell a complex story of quality, contamination, and environmental impact. As technology advances, so does our ability to peer into the microscopic world of water, unveiling the secrets hidden within each droplet. In this exploration, we will embark on a journey through the 9 most prevalent techniques for testing the solid particles in water. These methods, ever-evolving and diverse in their approach, provide a window into understanding the very substance that sustains us. Whether you're a scientist, a curious mind, or someone concerned about the water you consume, this guide will serve as a backbone to understanding the intricacies of water testing. So brace yourself as we dive into the fascinating world of water analysis, where each method reveals a unique perspective and each particle tells a tale of its own. Turbidity testing. Turbidity testing is a widely used method to assess the quality of water by measuring its cloudiness or haziness. This cloudiness is caused by the presence of suspended particles, such as silt, clay, microorganisms, and other organic and inorganic substances. The turbidity level is often considered an indicator of the overall water quality and can be used in various applications, including drinking water treatment, wastewater management, and environmental monitoring. How turbidity testing works. The principle behind turbidity testing involves shining a light through a water sample and measuring the amount of light scattered by the particles present in the water. The scattered light is detected at various angles, and the intensity of the scattered light is directly related to the concentration and size of the particles. The result is usually reported in nephelometric turbidity units, NTU, a standardized unit of measurement for turbidity. Equipment and methodology. Turbidity testing can be performed using a turbidity meter, which consists of a light source, a cuvette to hold the sample, and detectors to measure the scattered light. The sample must be carefully prepared, avoiding air bubbles and ensuring proper mixing. Calibration with standard solutions is essential for accurate measurements. Portable turbidity meters are available for field testing, while laboratory instruments may offer higher precision and additional features. Applications and importance. Turbidity testing is essential in various fields, including public health, environmental protection, and industrial processes. In drinking water treatment, it helps in monitoring the effectiveness of filtration and sedimentation processes. High turbidity levels may indicate the presence of harmful pathogens or pollutants. In environmental studies, turbidity is used to assess the health of rivers, lakes, and other water bodies, reflecting the impact of erosion, runoff, and human activities. Limitations and considerations. While turbidity testing is a valuable tool, it has some limitations. It does not provide information about the specific types of particles present and may not detect very small particles. Factors such as color and dissolved substances can also affect the readings. Careful sample preparation, calibration, and interpretation are essential to overcome these challenges and obtain meaningful results. In conclusion, turbidity testing is a versatile and accessible method for assessing water quality. Its simplicity, speed, and relevance to various applications make it a fundamental tool in water analysis. However, understanding its limitations and ensuring proper methodology is key to leveraging its full potential. Whether used in a laboratory, industrial setting, or in the field, turbidity testing continues to be a vital component in the pursuit of clean and safe water. Filtration followed by weighing the residue. Filtration followed by weighing the residue is a conventional method used to quantify suspended solids in water. It involves physically separating the particles from the water and then weighing them to determine their concentration. This method is commonly employed in water quality analysis, wastewater treatment, and various industrial applications where understanding the amount and nature of suspended solids is crucial. How the method works. The process begins by passing a known volume of water through a filter with a specific pore size designed to capture solid particles. Once the filtration is complete, the filter with the trapped residue is dried to remove any remaining moisture. The filter is then weighed before and after the filtration process, and the difference in weight provides the mass of the solid particles present in the sample. The concentration can be calculated based on the volume of water filtered. Equipment and methodology. The equipment required for this method includes a filtration apparatus, suitable filters, a drying oven, and a precision balance for weighing. The choice of filter material and pore size depends on the nature of the particles to be captured. Care must be taken to prevent the loss of particles during handling and to ensure complete drying before weighing. Calibration and proper maintenance of the weighing balance are essential for accurate results. Applications and importance. This method is widely used in various fields, including environmental monitoring, industrial quality control, and research. In wastewater treatment, it helps in assessing the efficiency of sedimentation and filtration processes. In environmental studies, it provides insights into soil erosion, sediment transport, and pollution. The method's ability to physically separate and quantify particles makes it a valuable tool for understanding the characteristics of water and other liquids. Limitations and considerations. While this method is robust and versatile, it has some limitations. It can be time-consuming, especially the drying process. The potential loss of particles during handling and the choice of filter material can affect the accuracy of the results. It may not be suitable for detecting very fine particles or dissolved substances. Careful procedure, appropriate equipment selection, and skilled handling are vital to mitigate these challenges. In conclusion, filtration followed by weighing the residue is a fundamental method for quantifying suspended solids in water. Its physical nature, adaptability, and direct measurement make it a reliable tool in various applications. However, awareness of its limitations and adherence to proper methodology are key to obtaining meaningful and accurate results. Whether used in a laboratory or an industrial setting, this method continues to be an essential technique in water analysis and quality control. Microscopic examination. Microscopic examination is a technique that utilizes microscopes to visually observe and analyze particles suspended in water. This method allows for the identification, counting, and characterization of specific types of particles, including microorganisms, algae, minerals, and other organic and inorganic substances. It plays a vital role in water quality assessment, environmental studies, and scientific research. How the method works. A sample of water is prepared, often by placing it on a glass slide or using specialized chambers, and then examined under a microscope. The magnification and illumination provided by the microscope enable the observer to see individual particles and study their size, shape, structure, and other characteristics. Special staining techniques may be used to enhance visibility or identify specific components. The particles can be counted manually or with the aid of image analysis software. Equipment and methodology. The equipment required includes a suitable microscope, which may be a light microscope, phase contrast microscope, or electron microscope, depending on the analysis needs. Additional accessories such as cameras and software may be used for digital imaging and analysis. Sample preparation, including filtration or concentration, may be necessary to obtain a representative sample. Skilled personnel with knowledge of the particles being studied are essential for accurate identification and interpretation. Applications and importance. Microscopic examination is widely used in various fields, including public health, environmental protection, and industrial processes. In drinking water analysis, it helps in detecting harmful pathogens such as bacteria and protozoa. In environmental monitoring, it provides insights into the ecological health of water bodies. The method's ability to identify and characterize particles at the microscopic level makes it a powerful tool for understanding the composition and quality of water. Limitations and considerations. While microscopic examination offers detailed insights, it has some limitations. It can be labor-intensive and time-consuming, especially for large samples or detailed analysis. Subjectivity in interpretation may lead to inconsistencies between observers. The method may not detect very small nanoparticles or dissolved substances. Careful sample preparation, appropriate equipment selection, and expert handling are vital to overcome these challenges. In conclusion, microscopic examination is a versatile and informative method for studying particles in water. Its ability to provide visual evidence and detailed characterization sets it apart from other techniques. However, the success of this method relies on skilled observation, proper methodology, and awareness of its limitations. Whether used for routine monitoring or in-depth research, microscopic examination continues to be an indispensable technique in the field of water analysis and quality assessment. Laser diffraction. Laser diffraction is a sophisticated technique used to measure the size distribution of particles in a sample, including those suspended in water. By analyzing the pattern of light scattered by particles when illuminated by a laser, this method provides detailed information about the size, shape, and other characteristics of the particles. It's widely used in various industries, including pharmaceuticals, food processing, and environmental monitoring. How the method works. In laser diffraction, a laser beam is directed at a sample containing particles. As the light interacts with the particles, it scatters in different directions, creating a diffraction pattern. The angles and intensities of the scattered light are detected and analyzed using mathematical algorithms to calculate the size distribution of the particles. The method can handle a wide range of particle sizes, from nanometers to millimeters. Equipment and methodology. Laser diffraction requires specialized equipment, including a laser source, optical components to shape and direct the beam, detectors to capture the scattered light, and software for data analysis. Sample preparation may involve dilution, dispersion, or other treatments to ensure a representative sample. Calibration with standard particles is essential for accurate measurements. The method is typically automated and can provide rapid results. Applications and importance. Laser diffraction is a valuable tool in various fields due to its precision, versatility, and ability to handle diverse particle types. In water treatment, it helps in monitoring the efficiency of filtration processes. In environmental studies, it aids in understanding sediment transport and pollution. In industrial quality control, it ensures the consistency of products containing particulate materials. Its non-invasive nature and ability to provide real-time analysis make it a preferred choice for many applications. Limitations and considerations. While laser diffraction offers many advantages, it has some limitations. It can be expensive, both in terms of equipment and maintenance. The method assumes spherical particles, which may lead to inaccuracies for irregularly shaped particles. Sample preparation and instrument settings must be carefully optimized to avoid errors. Expertise in optical principles and data interpretation is required for reliable results. In conclusion, laser diffraction is a powerful and advanced technique for particle size analysis. Its ability to provide rapid and detailed insights into the characteristics of particles makes it a vital tool in various fields. However, the success of this method relies on proper equipment, skilled handling, and awareness of its limitations. Whether used for research, quality control, or environmental assessment, laser diffraction continues to be a cutting-edge approach in the study and understanding of particulate materials. Dynamic light scattering. Dynamic light scattering (DLS), also known as photon correlation spectroscopy, is a powerful technique used to determine the size distribution of small particles in suspension or polymers in solution. By analyzing the fluctuations in the intensity of scattered light, DLS provides insights into the size, motion, and other characteristics of particles. It's widely used in various fields, including nanotechnology, pharmaceuticals, environmental science, and material research. How the method works. In DLS, a laser beam is shown through the sample, and the scattered light is detected at a specific angle. The particles in the sample cause the intensity of the scattered light to fluctuate over time. By studying these fluctuations using an autocorrelator, information about the size and movement of the particles can be determined. The Brownian motion of the particles is directly related to their size, allowing for precise size distribution measurements. Equipment and methodology. DLS requires specialized equipment, including a laser source, detectors, correlator, and temperature-controlled sample chamber. Sample preparation may involve careful dilution and filtering to avoid multiple scattering and particle aggregation. The method is highly sensitive to contaminants, so cleanliness and proper handling are essential. Calibration with standard particles and proper instrument settings are crucial for accurate results. Applications and importance. DLS is a valuable tool for characterizing nanoparticles, colloids, proteins, and other small particles. In water quality assessment, it helps in detecting and analyzing nanoscale pollutants and contaminants. In pharmaceuticals, it ensures the consistency and stability of drug formulations. Its non-invasive nature, ability to handle small sample volumes, and provision for real-time analysis make it a preferred choice for many applications, especially where precise size information is required. Limitations and considerations. While DLS offers high precision, it has some limitations. It is mainly suitable for small particles, typically in the nanometer range, and may not detect larger particles. The presence of multiple particle sizes can complicate the analysis. The method is sensitive to sample preparation and instrument settings, and expertise in data interpretation is required for reliable results. The cost of equipment and maintenance can be relatively high. In conclusion, dynamic light scattering is a sophisticated and highly sensitive technique for particle size analysis. Its ability to provide detailed insights into the characteristics of small particles makes it an essential tool in various scientific and industrial fields. However, the success of this method relies on meticulous sample preparation, proper equipment, skilled handling, and awareness of its limitations. Whether used for research, quality control, or environmental monitoring, DLS continues to be a leading approach in the study of nanoscale materials. Conductivity measurement. Conductivity measurement is a common technique used to assess the ability of water to conduct an electrical current. This conductivity is directly related to the concentration of dissolved and suspended solids, including salts, minerals, and other ions in the water. It serves as an essential tool in water quality monitoring, wastewater treatment, environmental studies, and various industrial applications. How the method works. Conductivity measurement involves placing electrodes in the water sample and passing an electrical current between them. The ease with which the current passes through the water is measured, providing a value for the conductivity. This value is influenced by the concentration and type of ions present, as well as factors like temperature and the purity of the water. The result is typically reported in units such as microsiemens per centimeter, USCM, or millisiemens per centimeter, MSCM. Equipment and methodology. The equipment required for conductivity measurement includes a conductivity meter, which consists of a probe with electrodes and a display or interface for reading and recording measurements. Calibration with standard solutions is essential for accurate results. Portable meters are available for field testing, while laboratory instruments may offer higher precision and additional features such as temperature compensation. Applications and importance. Conductivity measurement is widely used in various fields due to its simplicity, speed, and relevance. In drinking water treatment, it helps in monitoring the effectiveness of desalination and purification processes. In environmental monitoring, it provides insights into water pollution and salinity levels. In industrial processes, it ensures the quality of water used in manufacturing, cooling, and other applications. Its non-invasive nature and ability to provide instant readings make it a preferred choice for routine monitoring. Limitations and considerations. While conductivity measurement offers many advantages, it has some limitations. It is a non-specific method and cannot differentiate between types of particles or dissolved substances. Factors such as temperature, pH, and the presence of interfering substances can affect the readings. Careful calibration, appropriate probe selection, and consideration of influencing factors are vital to obtain meaningful results. In conclusion, conductivity measurement is a versatile and accessible method for assessing water quality. Its ability to provide rapid and direct measurements of ion concentration makes it a fundamental tool in various applications. However, understanding its limitations and ensuring proper methodology is key to leveraging its full potential. Whether used in a laboratory, industrial setting, or in the field, conductivity measurement continues to be an essential technique in the pursuit of understanding and managing water quality. Spectrophotometry. Spectrophotometry is a widely used analytical technique that measures the amount of light absorbed or transmitted by a substance. In the context of water analysis, it can be employed to detect and quantify various compounds, including organic and inorganic substances, pollutants, and specific ions. It's a versatile tool used in environmental monitoring, water treatment, research, and various industrial applications. How the method works. Spectrophotometry operates on the principle that different compounds absorb or transmit light at specific wavelengths. By shining a beam of light through a water sample and measuring the intensity of light that reaches the detector, the concentration of a particular substance in the sample can be determined. The absorption or transmission is directly related to the concentration of the substance, following Beer's law, and can be used to create a calibration curve for quantitative analysis. Equipment and methodology. The equipment required for spectrophotometry includes a spectrophotometer, cuvettes, and often specific reagents for colorimetric analysis. The spectrophotometer consists of a light source, monochromator to select the desired wavelength, sample holder, and detector. Sample preparation may involve filtration, dilution, or addition of reagents to induce a color change for specific compounds. Calibration with known standards is essential for accurate quantification. Applications and importance. Spectrophotometry is a valuable tool in various fields due to its sensitivity, specificity, and adaptability. In water quality assessment, it helps in detecting contaminants such as heavy metals, nitrates, phosphates, and organic compounds. In wastewater treatment, it monitors the efficiency of chemical and biological processes. Its ability to handle a wide range of substances and provide rapid analysis makes it a preferred choice for routine monitoring and specialized studies. Limitations and considerations. While spectrophotometry offers many advantages, it has some limitations. It may require specific reagents and sample preparation for certain analyses. Interference from other substances absorbing at the same wavelength can affect accuracy. Instrument calibration and maintenance are critical for reliable results. The method may not detect substances that do not absorb light in the detectable range. In conclusion, spectrophotometry is a powerful and flexible technique for analyzing water quality. Its ability to provide precise and targeted measurements of various substances makes it an essential tool in diverse applications. However, the success of this method relies on proper equipment, skilled handling, and awareness of its limitations. Whether used for compliance monitoring, research, or process control, spectrophotometry continues to be a cornerstone in the field of water analysis and environmental science. Particle counting. Particle counting is a technique used to determine the number and often the size of particles present in a liquid, such as water. It is employed in various fields, including water treatment, pharmaceutical manufacturing, environmental monitoring, and quality control. The method provides valuable insights into the cleanliness, purity, and overall quality of water by quantifying the particulate matter present. How the method works. Particle counting operates by passing a water sample through a sensing zone where particles are detected and counted. The detection can be achieved through various means, such as laser light scattering, electrical sensing, or imaging. The number of particles and sometimes their size and shape are recorded, providing a profile of the particulate content. The results can be expressed as the number of particles per unit volume. Equipment and methodology. The equipment required for particle counting includes a particle counter, which may utilize different technologies such as optical, laser, or electrical sensors. Sample preparation may involve filtration or dilution to achieve a suitable concentration for analysis. Calibration with standard particles of known size and concentration is essential for accurate measurements. Modern particle counters often come with automated features and software for data analysis. Applications and importance. Particle counting is widely used in various applications due to its direct measurement and adaptability. In water quality assessment, it helps in detecting contaminants and assessing filtration efficiency. In industrial processes, it ensures the quality of water used in manufacturing and cooling systems. In pharmaceuticals, it is crucial for maintaining sterility and compliance with regulations. Its ability to provide rapid and detailed particle analysis makes it a vital tool for quality assurance and process control. Limitations and considerations. While particle counting offers many advantages, it has some limitations. It may not detect very small or large particles outside the detectable range of the instrument. The presence of bubbles, aggregates, or dissolved substances can interfere with the readings. Instrument calibration, maintenance, and proper sample handling are critical for reliable results. The cost of equipment and the need for skilled operation may also be considerations. In conclusion, particle counting is a robust and informative technique for analyzing particulate matter in water. Its ability to provide quantitative and sometimes qualitative information about particles makes it an essential tool in various fields. However, the success of this method relies on proper equipment, skilled handling, and awareness of its limitations. Whether used for routine monitoring, research, or industrial quality control, particle counting continues to be a leading approach in the study and management of water quality. Acoustic techniques. Acoustic techniques utilize sound waves to detect, characterize, and monitor particles in water. By analyzing the interaction of sound waves with particles, these techniques provide information about the size, concentration, and other characteristics of the particles. Acoustic techniques are employed in various fields, including environmental monitoring, water treatment, sediment transport studies, and industrial applications. How the method works. Acoustic techniques operate by transmitting sound waves through a water sample containing particles. As the sound waves interact with the particles, they are scattered, absorbed, or reflected. The changes in the sound waves are detected and analyzed to determine the properties of the particles. The method can be adapted to study different particle sizes and concentrations, providing a versatile tool for particle analysis. Equipment and methodology. The equipment required for acoustic techniques includes a sound source, such as an ultrasonic transducer, receivers to detect the sound waves, and software for data analysis. The choice of frequency, waveform, and detection method depends on the nature of the particles and the specific analysis required. Calibration with known standards and careful alignment of the equipment are essential for accurate results. Modern systems may offer automated features and real-time monitoring capabilities. Applications and importance. Acoustic techniques are valuable in various applications due to their non-invasive nature and adaptability. In water quality assessment, they help in detecting contaminants and assessing the efficiency of filtration processes. In environmental studies, they provide insights into sediment transport and erosion. In industrial processes, they ensure the quality and consistency of products containing particulate materials. Their ability to provide rapid and detailed analysis without physical contact with the sample makes them a preferred choice in many scenarios. Limitations and considerations. While acoustic techniques offer many advantages, they have some limitations. They may be sensitive to factors such as temperature, salinity, and the presence of bubbles or dissolved gases. The method may require specialized equipment and expertise, particularly for complex analyses. Interpretation of the data can be challenging, and proper calibration and methodology are vital to obtain meaningful results. The cost and complexity of the equipment may also be considerations. In conclusion, acoustic techniques represent a sophisticated and powerful approach to particle analysis in water. Their abilities applications. However, the success of these methods relies on proper equipment, skilled handling, and awareness of their limitations. Whether used for research, quality control, or environmental assessment, acoustic techniques continue to advance the field of water analysis and contribute valuable insights into the understanding and management of water quality. Certainly, my apologies for the confusion. Here's the revised paragraph that will follow the explanation of the 9 different testing techniques, focusing on the upcoming series where you will demonstrate some of the methods and show how viewers can apply them. Having explored the 9 diverse techniques for testing solid particles in water, our journey now takes a practical turn. In the series that follows this foundational exploration, we will not only discuss but actively demonstrate some of these methods in action. You'll witness firsthand the testing we've conducted, revealing the fascinating intricacies of water analysis. But we won't stop there. Our goal is to empower you, the consumer, with the knowledge and tools to conduct your own testing using some of these techniques. Whether for personal understanding or to ensure the quality of the water you consume, this series is designed to make the science of water testing accessible and applicable to everyday life. Join us as we transition from theory to practice, bringing the world of water testing into your hands.
Human health impact of solid particles in water. Introduction to the problem water is essential for human survival, but its contamination with solid particles poses significant health risks. These particles can carry pathogens, heavy metals, or toxic chemicals, leading to various health problems when ingested. This discussion explores the human health impact of solid particles in water, focusing on the carriage of pathogens and the presence of heavy metals and toxic chemicals. Pathogens. Carriage solid particles in water can act as carriers for disease-causing pathogens, such as bacteria, viruses, and parasites. When contaminated water is consumed, these pathogens can lead to waterborne diseases like cholera, typhoid, and dysentery. The severity of these diseases can range from mild discomfort to life-threatening conditions, particularly in regions with limited access to medical care and sanitation facilities. Heavy metals and toxic chemicals. In addition to pathogens, solid particles in water may contain heavy metals like lead and mercury, as well as toxic chemicals. These substances can accumulate in the body over time, leading to chronic health issues such as neurological disorders, kidney damage, and cancer. Children are particularly vulnerable to these effects, as even low levels of exposure can have long-term developmental consequences. Conclusion and prevention. The presence of solid particles in water is a serious public health concern that requires immediate attention and action. Effective water treatment, regular monitoring, and public awareness are crucial in preventing the associated health risks. By understanding the nature of these particles and implementing proper safety measures, we can protect human health and ensure access to clean and safe water for all. Environmental impact of solid particles in water. Introduction to the environmental concern. The presence of solid particles in water is not only a threat to human health, but also a significant environmental concern. These particles can clog waterways, harm aquatic life, and alter the natural ecosystem. This paper delves into the environmental impact of solid particles in water, examining the effects on waterways and aquatic life, as well as the aesthetic and recreational implications. Clogging of waterways and impact on aquatic life. Solid particles can accumulate in rivers, streams, and lakes, leading to blockages and reduced water flow. This clogging can decrease oxygen levels in the water, creating dead zones where aquatic life cannot survive. Fish, invertebrates, and other organisms may be adversely affected or even killed, leading to imbalances in the ecosystem and potential extinction of sensitive species. Aesthetic and recreational impact. The accumulation of solid particles like algae, debris, and sediment can also affect the appearance and usability of water bodies for recreational purposes. Murky and polluted water deters activities such as swimming, fishing, and boating, impacting local tourism and community enjoyment. The aesthetic degradation of natural water bodies can have long-term consequences for the cultural and economic value of a region. Conclusion and mitigation. The environmental impact of solid particles in water is a complex and pressing issue that requires coordinated efforts to address. Implementing proper waste disposal, erosion control measures, and regular cleaning of water bodies can prevent the harmful accumulation of particles. Public awareness campaigns and collaboration between governmental and non-governmental organizations are also essential in preserving the ecological integrity and recreational value of our water resources. Water, the essence of life, can sometimes be tainted by solid particle contamination. But what are these particles, and where do they come from? Let's delve into the world of prevention and treatment to understand how we can keep our water clean and safe. Our journey begins with proper waste disposal. By ensuring that waste materials are handled correctly, we can prevent them from entering our precious water bodies. Recycling programs, lined landfills, and public education are key to this effort. But that's not all. Erosion control measures play a vital role in keeping soil and sediments from washing into water sources. Planting vegetation, using retaining walls, and stormwater management are just a few ways to combat this issue. Moving on, we must also regulate industrial and agricultural practices. By monitoring and controlling potential runoff, we can minimize the risk of contamination. Best management practices, regulations, and compliance are our allies here. Now let's explore the fascinating world of water treatment. Physical processes like sedimentation and filtration are the first line of defense, allowing solid particles to settle and be filtered out. But sometimes we need to go further. Chemical treatments, such as coagulation and flocculation, use specialized chemicals to bind particles together, making them easier to remove. And for those more challenging contaminants, advanced techniques like reverse osmosis and activated carbon filtration come into play. These methods offer a higher level of purification, ensuring that our water is free from even the most stubborn particles. Finally, we must not overlook the power of public awareness and stringent regulations. Education, campaigns, clear guidelines, and penalties for non-compliance all contribute to a comprehensive approach to controlling solid particle contamination. Together, these prevention and treatment strategies form a robust shield against solid particle contamination. By understanding and embracing these methods, we can all contribute to a future where clean and safe water is a reality for everyone.
Thank you for spending this hour with us, exploring the vital subject of water cleanliness. Your time and attention are not just appreciated, they're a testament to your commitment to understanding and preserving this essential resource. As we continue this series, we'll be venturing into local communities, testing water, and displaying the information for all to see. We invite you to join us on this exciting journey, where we'll uncover the truths about water quality in various locations. But we don't want this to be a one-sided conversation. We invite you, our viewers, to participate actively. Test your local water, share your results, and become part of a global community dedicated to water cleanliness. Your involvement can make a real difference, fostering awareness, collaboration, and positive change. So, please, return for the next episode and the ones that follow. Together, we can create a wave of understanding and action that ripples across the world. From all of us here, thank you once again, and see you in the next episode.